Right. So under electromagnetic induction, the topics that we're going to discuss today are going to be the definition of electromagnetic induction, Faraday's law, and Lenz's law. So what do you mean by the term electromagnetic induction? So electromagnetic induction is basically a phenomena by which when a conductor cuts a magnetic field, it induces EMF. Okay. For example, as you can see here, there is a conductor which is moving downward, cutting the magnetic field lines. There will be EMF induced in this conductor. What is called EMF? EMF is nothing but basically voltage. The full form for EMF is electromotive force, okay, which is also known as voltage or potential difference. Potential difference. Now, how do we know whether EMF is generated across this conductor or not? Since we have connected the two ends of the wire to an instrument called galvanometer, the deflection in the galvanometer will show whether the voltage is induced or not. So yes, what is EMF? What is electromagnetic induction? It is basically a phenomena by which a conductor, when cuts the magnetic field lines, produces EMF or EMF is induced in it. Okay, and this phenomenon is called as electromagnetic induction. Now, before we talk about Faraday's law, we need to understand a term called magnetic flux. So what is a magnetic flux? It is nothing but how much magnetic field lines are passing through a given coil. For example, if this is the coil and these are the field lines passing in this region, these are the field lines in this region. If I ask you, is every field lines passing through my coil? The answer is no. When these field lines are not passing through my coil, not this field line passing through my coil, only these field lines are passing through my coil. So the amount of field lines passing through my coil is called as flux, also known as magnetic flux, or people call it as flux linkage. The term denoted for flux is phi, that letter phi, which is given by the formula B into A, where B stands for magnetic field strength and A stands for area of the coil. Clear? Now, these are not the only two factors which affects the flux, but there are other two factors also. That is number of turns. Means if these are the field lines and I kept one coil which has a flux linkage of phi, and I have another coil, will have another flux linkage of phi, third coil, phi, fourth coil, phi. That means how much magnetic field linkage? Each coil phi, that means four coil will be four times phi. That means number of turns increases the flux linkage. More the number of coils, more the number of turns means more the flux linkage. And finally, theta is also one of the factor. Means if these are the field lines and I have kept my coil parallel to the field lines, that means none of the field lines are passing through my coil. No, passing through means inside. It should go through the loop. So when you place parallel to the field lines, none of the field lines are passing through the loop, right? So what if I keep the loop perpendicular to the field lines? Then the flux linkage is said to be maximum. If I keep parallel to the field lines, then we say flux linkage is zero, right? So if the angle is zero, angle is measured with respect to the normal of the coil, if that's called normal of the coil. And you can see if the angle made by the normal is 0 degree or 180 degree, then the flux linkage is said to be maximum. Whereas if the normal of the coil is making 90 degrees to the field lines, then we say flux linkage is zero. So I'm drawing a graph for flux versus angle. When theta is zero, as I said, theta being 0 or 180, the flux is maximum phi naught. Whereas when theta is 90, the flux is zero. So the graph goes like this. And what type of graph is it? It's cosine graph. That's why the flux depends on cos of the angle. Clear? Next. So question, a loop of area 8 centimeter square is in constant magnetic field B. The value of B is given to you. The unit for B is Tesla. What is the magnetic flux through the loop when the loop is perpendicular to the field? So loop is perpendicular to the field, not the normal. So when the loop is perpendicular to the field, that means normal is making an angle 0 degree, right? When the loop is perpendicular means normal is making 0 degree, correct? If normal is making 0 degree, that means the flux will be maximum because from the formula flux is equals to BAN cos theta, which is cos 0, which will be equal to BAN since cos 0 is equals to 1. So value of B is given, yes, 0.15 Tesla. The value of area given, yes, but it is in centimeter square. It has to be converted into meter square. So 10 to the power of minus 4 meter square times the number of loop. It is just one loop, a loop. So if you simplify all this, your answer will be 1.2 times 10 to the power of minus 4 Weber. So please note that the unit for flux is Weber, WEBRE, in short, WB. Whereas the loop is parallel to the field, that means normal is perpendicular to it. When normal is perpendicular, what will be theta? 90 degree. So cos 90 is 0, so flux will become 0. Okay, next. Let's talk about Faraday's law. What Faraday's law state is that the EMF induced, we said no, that if a conductor cuts the magnetic field, if these are the two magnetic magnets, one is north, one is south, and we have a field lines going from north to south, and there is a conductor which cuts the magnetic field. If you're making the conductor move down, you know this conductor is going to cut this magnetic field. So there will be EMF across this conductor. The question is how much EMF will be across the conductor? So Faraday law answered it. Faraday law states that the EMF induced across the conductor is proportional. EMF is denoted with letter E like this, is proportional to the rate of change in flux. That means at what rate the flux is changing decides the EMF is how much EMF is going to be induced. So what do you mean by that? So let's talk about what do you mean by rate of change in flux. Rate of change in flux means because since flux is equals to BAN cos theta, so if your B is changing, or area is changing, or number of turns is changing, or theta is changing, in any case, if any one of them is changing, or if any one or more than one is changing, there will be change in flux. Okay, but at what rate they are changing will decide the EMF, not just if they're changing or not. Yes, they must be changing, then only flux will be changing, then only EMF will be there. But on the top, not just flux needs to be changed, but at what rate the flux changes decides the EMF. For example, if there's a flux change of 5 Weber and that flux change takes place in 2 seconds, whereas for second student, the same flux change 5 Weber happens in 1 second, here the EMF induced will be 2.5 volt. Here the EMF induced will be 5 volt. So what you understand is it's not just the flux change decides the EMF that is going to be induced, but also at what rate the flux has changed. That means how long it took to change that flux. Okay. So yeah, and that gives the Faraday's law. So writing down the Faraday's law, so Faraday's found that the induced EMF is equal to the rate of change in magnetic flux linkage that is given by the formula E is equals to n d phi by dt or delta phi by delta t. What is delta phi? Change in flux. Delta t, time period. N, number of turns. Now, the magnetic field through a single loop of area 0.20. Single loop means n is equals to 1. Area given as 0.20 meter square is changing at a rate of B is equals to 4.0 Tesla per second. Wait, it is just B value or B by T value? It is B by T value. How do we know that? Because it is Tesla per second, not Tesla. The unit for B is Tesla, whereas the unit for B by T will be Tesla per second, no? So that means it is B by T value. What is induced EMF? So EMF induced is N delta phi by delta T. And what is delta phi? I mean, what is phi? Phi is BA, okay? Cos theta I'm ignoring because they have not talked about the angle. So I'm ignoring the value of cos theta divided by delta T. Is the value of area constant? Yes, it is constant area. It is not changing. So I'm pulling it out. So what will be left inside the bracket? It will be delta B by delta T. What is delta B by delta T means? It means at what rate the magnetic field strength is changing. And it is given as 4 Tesla per second. The number of turns, one single loop, area 0.20 meter square. The rate at which the magnetic field strength is changing, it is 4.0. Simplifying that will give you 0.80 volt. So what is the learning from this problem? That is EMF induced, which we generally write as N delta phi by delta T, which has to be written later as what is phi? It is BAN, sorry, not N, because N is not there anymore. It is being taken out into cos theta. So if they're not talking about angle, that means cos theta can be taken as 1, which will be followed as delta of BA. Now, when one of them is constant, in this case, if area is constant, we can pull that out. We'll leave it delta B by delta T. Clear? So if everything is given, you substitute, you'll get the answer. Okay, next. A pair of conducting rails is placed in uniform field, 0.40 Tesla. That means the value of B is given, as shown in figure. The rails are at a distance of 0.20 meters. Okay, so length of the rail is given. The length of the conductor is given. A rod is placed on the rails and pushed to the right at a constant speed of 0.60 meters per second. So rail is taken with the speed of 0.60 meters per second. What is the induced EMF in the loop formed by the rod and the rails? So again, I'm going to write the basic formula. EMF is equals to N delta phi by delta T. So it is just one loop, so N is 1. Carry forwarded with what is phi? BA cos theta. Since the magnetic field lines are perpendicular to the loop, the magnetic field lines are going into the page. If the magnetic field lines are perpendicular to the loop, means magnetic field lines are parallel to the normal. We measure the angle with respect to the normal, but not with the loop. So when theta is 0 degree, cos 0 will be 1. So that is also ignored. That means delta BA by delta T. Now we'll see, is B constant? Is the magnetic field strength constant? Yes, 0.40 it is constant. So pulled out, you're left with delta A by delta T. Is area of the loop changing? The answer is yes. Why? Because this conductor is moving to the right. When this conductor is moving to the right, obviously the loop area is changing. In this change in loop area, is that area of the loop changing due to the change in length or due to the change in width? The answer is it is changing due to the change in width because the length is constant. The length is not changing, right? Now, I can write this as d times what? Area can be written as length into width divided by time. Since length is constant, I'm taking it out of the bracket. You left with delta W by delta T. What is delta W by delta T stands for? At what rate the width is changing. The rate at which the width is changing is basically the speed with which the rail is moving. So what is the speed with which the rail is moving? 0.60 meters per second. That means the width is changing by a rate of 0.60 meters every second. So delta W by delta T is 0.60. Value of B is given, length is given, delta W by delta T is 0.60. If you solve it, you'll get the answer as 48 meter millivolt. So what is the learning from this problem? The learning from this problem is that delta phi can be either due to change in B or can be due to change in area. Now, if it is only due to change in area, again, area can be due to change in length or width or maybe due to both. We don't know. But examiner will only test on one factor. So in this case, since length is constant, I pulled it out of the bracket. The change is only in the width. So since the change is only due to the width, I kept width inside the bracket and everything is not changing. They're constant, so pulled out of the bracket. That's the learning objective from this problem. Now, Lenz law. So what Lenz law state is that whatever EMF induced, Faraday has said that it is proportional to the rate of change in flux. It is right, but that EMF induced in the coil always opposes the change in flux. For example, say I have a loop and there is a magnet not approaching the loop. So because the magnet is approaching the loop, the strength of the magnetic field is increasing. That means there's a change in magnetic field strength. Because magnet is getting closer and closer, means stronger magnetic field will be experienced by this loop. And that change in magnetic field strength will lead to change in flux. That will lead to EMF to be induced in the loop. So what Lenz has stated that whatever the EMF that is going to be induced in this loop, which will lead to flow of current in the loop, the current will be in such a way that current which will produce a magnetic field around the loop, because, so what are you talking about? Why will current produce magnetic field? I mean, you know that a current carrying coil produces magnetic field around it, right? A current carrying conductor also produces magnetic field around it. So whenever there's a current flowing in the conductor, it produces magnetic field. And what Lenz is trying to say is that whatever the EMF induced, which leads to flow of current in the loop, that current will produce the magnetic field in such a way that it will oppose the cause. So what is the cause producing this current? It is the magnetic field which is approaching, means magnet is approaching. Because the magnet is approaching, the current is induced. That means magnet approach is a cause, current induced is a result. So in my layman term, the result opposes the cause. Means whatever the current that is induced in the coil will oppose the magnet which is approaching. Right. So it is clear. What if the magnet is going away? Means what if the magnet is taken away? Then again, because the magnet is taken away, the bees this time is reducing. That means there's a change in value of field strength. That will lead to change in flux. That will lead to EMF to be induced in the coil. That will lead to flow of current in the coil. The flow of current in the coil will be in such a way that it will oppose the cause. What is cause doing? The cause is going away. I'm writing down here. The cause is going away. The magnet is going away. What will result, which is current, will do to that magnet? It will say, I will not let you to go away. I will try to pull you back. That will make south to be generated on the left side of the coil and north to be generated on the right side of the coil. Why south is generated on the left side of the coil? In order to pull that magnet. Because magnet is trying to go away, lens says that no. The EMF induced in the coil will not let that magnet go away. And when the magnet was trying to approach, then the coil will not let the magnet to approach, which will make north to be induced on the left side and south to be induced on the right side, which will cause repulsion between them. Here it is causing attraction, here it is causing repulsion. So in simple terms, Lenz's law states that the induced EMF will be in such a direction as to oppose the change in magnetic flux that created the current. It is equivalent to energy conservation. Basically, it is supporting that energy conservation. So how is it supporting the energy conservation? Just we'll look at it. For example, if the magnet is coming closer, the B is increasing. That increase in B will keep on increasing the value of current, right? But if this magnet which is moving, will it move forever? If it moves forever and ever, that means it is accelerating forever. That means the current will induce forever and increasing forever. I mean, according to law of conservation of energy, energy needs to be just conserved. Means whatever the movement you're making the magnet to move means you're putting a mechanical energy into it to make this magnet move. And that mechanical energy is converting into electrical energy in the coil. If electrical energy is increasing, that mechanical energy must be reduced. That means movement must be reduced. That means this magnet should slow down. But who will do that? Who will make the magnet to slow down? It is the coil that will do it, according to Lenz's law. Means it is equivalent to energy conservation, right? Perfect. So that's about Lenz's law. And how is the Lenz's law in the formula? The negative in the formula. Okay. So what does negative stands for here? That the EMF induced is always opposite to the rate of change in flux. Now, a loop of wire has its plane horizontal and a bar magnet is dropped from above so that it falls through the loop with the north pole first as shown in the figure. Find the direction of the current induced in the loop. Okay, so we'll see. As north is approaching, the loop will make sure that because it is coming closer, right? The magnet is trying to come closer to the loop. But what will loop do to it? It will say, no, go away. I will not let you come closer. That's what Lenz's law states. And this can only be possible by having a north pole on the top in the coil and south pole at the bottom of the coil. Now, by using right hand grip rule, right? By using right hand grip rule, we know that the thumb shows the direction of the north and finger shows the direction of current induced in the loop. So having north pointing on the top and fingers shows the direction of current in the loop. That's the direction induced in the current. Okay, that is the direction of current induced in the loop. It's clear? That's what I said, the direction of current induced in the loop. Now, what if the magnet is going away? When the magnet is going away, that means south pole is going away. I'm writing down here. South pole is going away. What will coil say according to Lenz's law? I will not let you go away. I will not let you go away. That is the meaning of opposing, no? Lenz's law states that the EMF induced always opposes the cause. So because the magnet says I want to go away, loop says no, you can't. And that can only be possible by having north induced at the bottom of the coil and south induced on the top of the coil. And by using your right hand grip rule, that's how the thumb is pointing down, by having north at the bottom, and finger shows the direction of current induced. That's how the current is induced. Next, a large coil has a small, a large coil has a small coil inserted inside it so that their axes are parallel. Okay. The smaller coil has 200 turns and the diameter of 2 centimeter. A change in current in the large coil causes the magnetic field to be increased at a rate of this. Calculate the EMF induced in the smaller coil. So we know that the EMF induced in the smaller coil is given by N into delta phi by delta T. Okay. So what is, I mean, delta phi, I'm replacing that delta phi with delta of BA. Since they're not talking about the angle, it will be 1 by delta T. Is the value of B changing? We'll see. Yeah. A changing current is the coil causes the magnetic field to increase. That means magnetic field is changing. The value of B is changing. So area will be pulled out of the bracket. You're left with delta B by delta T. At what rate the value of B is changing? 0.45 Tesla per second. So delta B by delta T is 0.45. So value of area can be calculated from the diameter, the number of turns given as 200, and the value of delta B by delta T is 0.45. Solving that, your answer will be 28 millivolt. Next. So similarly, you can solve this problem. I'll share this PPT. Okay, so the flux through a loop as a function of time is given by the graph in the diagram. Sketch a graph of the EMF induced in the loop as a function of time.
Okay.
So question here is they have given you flux versus time. So what is the slope gives you? Slope is basically your change in y by change in x. Change in y is your change in flux. Change in x is change in time. And we know that change in flux by time is called EMF. That means slope gives you EMF. And what is the slope of the straight line? Constant slope. How much you can calculate by using change in y by change in x. Means how much rise? Rise is about 20, but run is about 10. So slope is 2. So we'll plot a graph of EMF versus time with a constant value of EMF, which 2. So why constant value of EMF you're drawing? Because slope is constant. Slope is EMF. Next. This time, instead of giving you, this time also they have given flux versus time, asking you to draw the EMF graph. So we know that EMF is slope of the graph. So what is the slope from A to B? Slope from A to B is 0. Slope from B to C is negative, but how much? Rise by run. So 8 to 4 is 4, divided by run is 6. So negative 4 by 6. And C to D is, again, rise 4 to 0 is 4, run is 4, negative. So negative 1 slope. So you can see initially slope 0, then slope of 2, about 2, and then slope of 1. Next. The graph shows the EMF induced in the loop as a result of changing flux in the loop. Sketch a possible flux versus time graph that would give you the rise to such of EMF. So they have given you this. This is actually answer. Please ignore it. They have given you EMF versus time graph and asking you to draw the flux versus time graph. So what is EMF? Rate of change in flux. So what is change in flux? EMF into change in time. So isn't it EMF is a y-axis quantity here and time is the x-axis. So y quantity into x quantity is always area under the graph. So area under the graph will give you change in flux. So what is area under the graph here? 6 4 is 24. That means the change in flux over here should be 24. What is the area under the graph from 4 to 8? 0. So change in flux from 4 to 8 should be 0. What is the area under the graph from 8 to 12 second? So 12 into 4. 12 4 is a 48. So change in flux should be 48. As you can see, the graph started from 0. The change in flux should be 24. So it should be go to until 24. And then from 4 to 8 seconds, the change in flux is 0. That means it should remain constant 24. This should, why sir? Because change in flux should be 0. And then from 8 to 12, the change in flux is to 48. So 24 to 48 is 72. So that's how you draw the graph from EMF to flux or flux to EMF. Next, the diagram shows the top view of two solenoids, which is two coils, with their axes parallel, one with a smaller diameter so that it fits inside the other. The bigger solenoid has a current flowing in the clockwise direction, and the current is increasing the magnitude. Find the direction of induced current in the smaller solenoid. So what are they saying? The current is increasing here. Increase in current means the change in current is positive, right? When change in current is positive, that will produce change in flux, which will also be positive. And what will be EMF induced in the smaller coil? So according to the formula, EMF in the smaller coil will be negative N into delta phi by delta T. N is anyways 1, delta phi it is positive, and the formula has a negative. That means EMF induced will be negative into positive, being negative. That means the EMF induced in the smaller coil will be opposite to the EMF in the bigger coil. That means the current should be opposite. Why, sir? Because the EMF should be negative. So a negative EMF means opposite current. What if the question says in the exam, the current is not increasing but decreasing? So when the current here is decreasing, means change in flux is negative. So from the formula, EMF is equal to negative N delta phi by delta T, since N is constant and delta T is constant, and delta phi it is negative. So negative multiplied by the negative in the formula makes EMF to be positive. That means whatever the direction of current you have in the primary coil, same direction of current will be in the secondary coil.
That makes sense.
Yeah, next.
Yeah.
Find the direction of current in the loop shown in the diagram as the current in the straight wire is increasing. So current in the straight wire is increasing. Means change in flux is positive. That means EMF induced in this coil should be negative. That means current in this coil should be opposite. Because the current is going to the right, closest ways, the current should be left. That's how the current should be. But second question is, what if the current is decreasing? Decrease in current means change in flux is negative. Means EMF will be negative into negative, positive. So then the EMF will be in the same direction. So I will draw that with the red ink. EMF will be in the same direction as the current here. So you know how to say it's clockwise or not counterclockwise. Okay. So question here. A coil of area A is placed in a region of uniform magnetic field B. At time t0, the coil starts to rotate with constant angular speed omega about horizontal axis. What is the EMF between X and Y? So first of all, what is the normal making an angle with the field lines? It's 90 degree. Because when the loop is making an angle 0 degree, when the loop is parallel to the field lines, normal is making 90 degree. And according to the formula, EMF induced is N into delta phi by delta T. And delta phi depends on B into A into N into cos theta. So N is anyways taken out in delta T. Since theta is 90 degree, cos 90 will be 0. So EMF induced will be 0 between X and Y. Okay, next. So let's talk about the next topics, that is power in AC circuits and AC generator. Before that, there is a formula to be discussed that because see, we said EMF induced due to the process called electromagnetic induction. And we said how much EMF induced, that is according to Faraday's law, N into delta phi by delta T. And there's a negative in the formula due to the Lenz's law. So I'm going to take a conductor. Okay, I'm going to take a conductor and make it move to the right. The length of the conductor is L. Width of the conductor is W. So I'm assuming that the conductor of width W and length L is taken into the magnetic field region. So that means when you take this conductor inside the magnetic field region, the length is not changing. It's the width that has been exposed to the field lines is changing. Because while the conductor is entering, maybe only half of the width is exposed to the field lines. When the entire conductor is inside the field line, the entire width is exposed to the field lines. That means what is changing here is the width of the conductor changing with respect to the magnetic field. So what I can write, EMF is equals to N into delta into BA cos theta by delta T. Since B is changing, but area of the conductor being exposed is, since B is constant, but area of the conductor being exposed to the B is changing, right? So what I can write area as, I'm taking B outside, area can be written as length into width of the conductor, assuming the conductor is a what? Rectangular shaped. So length into width of the conductor divided by delta T. So at what rate the width is changing? The answer will be obviously the speed with which the conductor is moving inside. So I can replace that with N into B into L into V. Since the conductor is only one, so number of turns is one. So formula for EMF will be BLV. I'm writing down here. The formula for EMF is BLV. Okay, this is one formula. Or, or we can also derive like this. Since EMF we have written as N delta phi by delta T, whereas in calculus we write N into d phi by dt, which is what is phi? It is BA cos theta, right? So I can write this as N into BA d by dt of BA cos, since I'm not changing the values, will be d phi by dt, I mean d into d by dt of BA. So taking area of the B constant, so it will be dA by dt. What is dA by dt? Rate at which area is changing. It is changing due to the value of speed with which the conductor is moving inside, and that is changing the width being exposed. The length being exposed is always constant. The width being exposed, it can be only half width being exposed to the field lines or full width being exposed to the field lines, but the length is always same. So I'm talking in terms of calculus, but whether it is form of calculus or just writing in form of delta by delta of BA, it's the same thing, no matter whatever it is. So conclusion is that EMF induced according to Faraday law is N into delta phi by delta T, which can also be written as BLV. And that formula is there in your data booklet. Let me quickly show. Yeah, and that's the formula for EMF. So EMF induced in a straight conductor is given by the formula BLV, where B stands for magnetic field strength, V stands for speed with which the conductor is moving, and L stands for the length of the conductor. Now, so let's move to the next topic, that is power in AC circuits and AC generator. So we know that we're talking about AC circuits. What is meant by AC first of all? This type of current is called direct current, where the current is either clockwise forever with positive current or anti-clockwise forever with negative current, but never become clockwise to anti-clockwise or anti-clockwise to clockwise periodically. But with alternating current, positive peak represents the clockwise current and negative peak represents the anti-clockwise current. Again, the current becomes clockwise, again the current becomes anti-clockwise. So if the current direction is changing periodically, we call that current as alternating current. And if the current direction is constant, never change, clockwise remains clockwise forever, we call that source of current as direct current source. Okay. So this is how the alternating voltage graph looks like. That means the voltage is changing with respect to the time. And this is how the alternating current represented. That means the current is changing with respect to the time.
Hmm.
Okay. Now, the magnitude value, this highest value is called as peak voltage here, and the highest current over here is called as peak current. And the product of this peak current into peak voltage is called peak power. Clear? That means the
Yeah.
peak voltage into peak current, the product of that is called as peak current. I mean peak power. And when they're asking you what is the average power, obviously you divide that with two, right? You divide that with two to get the average power. So why you have to divide with two? So look at the function of the power. How does it look like? So voltage multiplied by current, isn't every negative value multiplied with negative makes it positive, and every positive value here multiplied with positive makes it positive. That means there is no negative graph for power. It is going to be pure positive graph like this. It will become like this with a peak value of how much? V naught into I naught, because product of both. So when I'm asking you what is average, obviously the average stands for this, the mean. Isn't that half of V naught into I naught? So the peak power is V naught into I naught, whereas average power is V naught into I naught by 2. Yeah. Next. So let's talk about AC generator. So what is AC generator? It is nothing but a device that converts mechanical energy into electrical energy. And if that electrical energy is alternating current, we call this as AC generator. Okay. So we'll see how does this AC generator function. So we just learned something that if there is a north pole and there's a south pole, and there's a magnetic field lines going from north to south, and you keep a conductor like this and we're making the conductor go down. So when this conductor cuts the magnetic field, we know that there is EMF induced in this conductor that leads to current to flow in the conductor. So, but we don't know whether the current will be X to Y or Y to X. But we know one thing, that EMF induced in this conductor will be B into L into V. Or according to Faraday's law, it will be delta phi by delta T. But we don't know the direction of current induced in this conductor. And we don't know whether it is X to Y or the current is from Y to X. To find the direction of current in this conductor, we are going to use right hand palm rule. So what is the right hand palm rule? We're going to keep all the fingers straight except for thumb of your right hand. The thumb shows the direction of force, I mean, in which direction the conductor is moving. The finger shows the direction of magnetic field, and the face of your palm, I'm talking about face of your palm, in which direction the palm is facing, that shows the direction of current. So, because you're making the conductor to move down, your thumb should be pointing downward. And since your magnetic field lines are to the right side, all your fingers of your palm must be pointing to the right side. Now, if you do this, you'll find your palm facing out of the page towards you, towards not towards the screen, but towards you. That means the current in this conductor will be from Y to X. That's how we find the direction of current. I repeat, electromagnetic induction says that when a conductor cuts the magnetic field, EMF is induced. So we learned about that. Faraday's law says that how much EMF is induced, which is delta phi by delta T, which also leads to another formula BLV. And then finally, the right hand palm rule tells us what is the direction of current induced due to that EMF. Because EMF is nothing but voltage. So where there is a voltage, there will be current flowing in that loop. So in which direction the current flows? It is demonstrated, it is derived from right hand palm rule. So keeping that in mind, we will talk about AC generator. So you can see there's a north here and there's a south here. I'm assuming that the coil is moving like this. That means CD is moving into the page and conductor EB is moving out of the page. So we will apply the right hand grip rule on the conductor AB. So since the conductor is moving out of the page, the conductor AB is moving out of the page. So your thumb should be pointing towards you. Your thumb should be pointing towards you. And your magnetic field lines are going to the right, north to south, right. So all your fingers should be pointing to the right. And you'll find your palm is facing upward like this. And the direction of the palm shows the direction of current. And that's why the direction of current is shown as A to B. And since CD is moving in opposite direction, because AB was moving out of the page and CD is moving into the page, reversing the direction of motion reverses the direction of current. Since the current was going up A to B, now here the current will be going down C to D. So you can see how is the current flowing. A to B, B to C, C to D, come back to this slip ring. This thing is called slip ring and goes to the brushes. That small black thing is called brushes, goes to the load. So what direction is the current flowing to the load? It is to the right. Okay, that is one half rotation. So after one half rotation, conductor AB comes to the right and conductor CD goes to the left. But your rotation does not change. Means this time CD will be going out of the page and AB will go into the page. Since you did not change the angle of rotation, since you did not change the direction of rotation, your direction of current induced will remain same only, no? That means on the left side, the current will be out upward and the downside. On the right side, the current will be downward. So complete the direction of current, D to C, C to B, B to A, goes to this slip ring and to the brush. And what is the direction of current with respect to the load? It is to the left. Previously, the current was to the right, now to the left. So what is happening to the direction of current is reversing. Since the direction of current is reversed due to the load, with respect to the load I'm talking about, the direction is not reversed in the coil, but the direction of current has been reversed with respect to the load due to all the setup kept here, which makes this current to be called as alternating current because current is reversing. And therefore, this generator is called as AC generator, alternating current generator. Okay, so that's basically the end of your Topic E3, but we'll end with this last question. The graph shows the variation with time of power delivered by an AC generator. State the frequency of rotation of the generator. So frequency of rotation means at what speed rate the something is rotating, right? So frequency
Yeah.
is nothing but 1 over time period. So what is the time period? Time period is nothing but time taken to complete one oscillation. That's time period for one oscillation. 20 millisecond. So 1 divided by 20 milli is 10 power of minus 3 seconds. If you simplify that, your answer will be 50 hertz. Next, on a copy of the graph, sketch the graph of a power delivered when the frequency of the rotation is halved. When your frequency gets half, time period gets doubled. So why? Because frequency and time period are reciprocal to each other. So time period gets doubled. Means the starting of the graph and end of the graph. One complete oscillation should get complete in 40 millisecond. And that's the graph for the power delivered when frequency of the rotation is half. And that brings finally to the end of electromagnetic induction.
Hmm.